Hey super scientists, we're looking in your periodic table lab notebook at page 10, and we're going to be talking about how to make Bohr models. So Bohr models are a specific type of atomic model, and this little timeline is just showing you some different models that scientists have developed throughout history. So scientists use models for things that are invisible or things that are too small to be manipulated or to have their characteristics examined. So as knowledge progressed about atoms, so too did the atomic models, and the models changed in order to reflect what scientists were learning. So you started out with this model 1803, this solid sphere. So basically scientists knew that atoms existed at that point. Then you have this plum pudding model. So here scientists knew that there was something positive and that there was something negative. They knew that there were different charges. And so that's represented in that particular model where everything's just kind of mixed up. This is the one that most people think of when we think about chemistry or atoms, this Rutherford model. And so at this point, scientists knew that electrons existed and that they kind of moved around the nucleus, because you can see the nucleus is represented there. And this is the Bohr model, so this is the one we're going to be focusing on, and we're looking at the placement of the electrons. So you have in this planetary model, the Bohr model, which is named after Niels Bohr, the scientist that developed it. So you have the nucleus in the center where you have your neutrons and protons, and then you have orbital shells, and those reflect the location of the electrons. So as we are placing our electrons on our Bohr model and on these orbital shells, we have to take into account the number of electrons, how many electrons can be contained in each orbital shell, and our valence electrons. So the valence electrons, this term here, the valence electrons are the electrons that are housed on the outermost orbital shell. So all of the electrons on the first orbital shell, second orbital shell, and so on are the core electrons, and the very outermost orbital shell contains what's termed as the valence electron. So on this blue ring that you see here, that's the valence shell, and it's going to have the valence electrons. And the valence electrons are important in bonding, so in chemical bonds that are taking place as different elements react together. So in this particular model, we have our nucleus that's represented right here with the blue circles and the yellow circles. And then this is our first orbital shell, so it has our 2 electrons. The green circle here is our second orbital shell. And then our blue ring here, that is our valence shell that has our valence electrons on it. So the electrons are important in helping, or the valence electrons specifically are important in helping atoms of different elements to bond together. And that's what we see represented right here in this example of CH4. We have 1 carbon atom, and then we have 1, 2, 3, 4 hydrogen atoms. So they are bonded together and sharing those electrons. So the red electrons are the ones that are from hydrogen. So you have a hydrogen electron represented those 4 corners, and then the blue electrons are the ones from carbon. So they're sharing those electrons as they're bonded together. So let's count the electrons really quickly and see how many we have total. 1, 2, 3, 4, 5, 6, 7, 8. So 8 is kind of the magic number, and we're going to talk about why in just a second. So as you're making your Bohr models, there's a specific amount of electrons that can be contained on each orbital shell. So the first orbital shell can hold a maximum of 2 electrons. It can hold less than that, but it can't hold any more than 2. The second orbital shell contains a maximum of 8 electrons. Third orbital shell contains a maximum of 18. Fourth orbital shell contains a maximum of 32 electrons. Fifth orbital shell contains a maximum of 18 electrons, and the sixth orbital shell contains a maximum of 8 electrons. So what this is saying is that as you are placing the electrons onto your Bohr model on these orbital shells, you basically have to fill up 1 orbital shell before you can put electrons on the next orbital shell. So for example, if we need 3 electrons represented on this atomic model, we could put 2 on the first orbital shell, but the third one wouldn't fit. So then you'd have to draw another ring, and that's why you have the next orbital shell, so you can place the next electrons on those orbital shells. So the valence electrons are really important in how atoms will bond with one another. We have this example of a water molecule, and we have oxygen right here, and then we have 2 hydrogen. So we know H2O makes up a water molecule. So let's look at the electrons. In the first orbital shell for oxygen, we have 2 electrons. And the second orbital shell, our valence shell, we have 1, 2, 3, 4, 5, 6 electrons. So what's going to happen is as the hydrogens bond with the oxygen, the electron that we see here is going to be shared with the hydrogen and the oxygen, and then we have this other electron that's going to move in here and it's going to be shared as well by the hydrogen and the oxygen. So the total amount of electrons that we have shared is 1, 2, 3, 4, 5, 6, 7, 8. So 8 is the magic number. 8 electrons is what's going to be shared as those elements are bonded together. So let's look at sodium and chlorine. Sodium is Na, chlorine is Cl. So how many valence electrons do these elements have? Let's look at sodium and count. So this is our valence shell. So the outermost shell here is going to have the valence electron. So we just have 1. And then for chlorine, this is our valence shell. So we're going to have 1, 2, 3, 4, 5, 6, 7. We have 7 electrons that are valence electrons for chlorine, and then our 1 electron that's a valence electron for sodium. What number do we get if we add those together? 1 plus 7 is 8. So sodium and chlorine like to combine together to make sodium chloride, NaCl. So if you saw what happened just there, the electron is being shared, so that completes the valence shell for chlorine, and that also allows for sodium to share those 7 electrons. So as they are bonded together, they are literally sharing those electrons. So valence electrons are really important in the pattern that we see reflected here on the periodic table as well. So if you look at group 1, so this is hydrogen and then our alkali metals. This 1 represents the amount of valence electrons that those atoms will have. And then over here on the noble gas side, you can see we have 8, 8, 8, 8, 8. So on this side, the group 18 elements, the noble gases, are going to have a complete outer shell. That's why they don't like to combine. That's why they're inert. They're not reactive, because they have a full outer shell and they don't want to mess with any other elements. They just want to be left alone. So the noble gases are happy little elements. They don't combine with other elements because they have this full outer shell. If we look at our example of sodium and chlorine using this periodic table, sodium is an alkali metal, so it is found in group 1. So it's going to have 1 valence electron. And then on this side, we have chlorine in group 17. So it has 7 valence electrons. So that's why those like to combine together, because 7 plus 1 equals 8. And you can see that represented here by Lewis dot diagrams, which is something you'll do in high school. But I like this picture because it shows what are some other common elements that these particular elements would like to combine with in making compounds. So for example, we know that hydrogen just has 1 electron as its valence electron, so it likes to combine with lots of other stuff, or other things like to combine with it specifically. So if you look at fluorine right here, fluorine has 1, 2, 3, 4, 5, 6, 7 electrons that are valence electrons. So it's just missing this 1 right here to make it a happy little compound. So this hydrogen here nicely fits in right there. So you can see that's the case for a lot of different elements, is that hydrogen fits right in there because it just has the 1 electron. So this magic number of 8, this is the octet rule. So for an element to be a nice little happy element, it wants to have 8 valence electrons. 8 is the magic number because that will fill up the valence shell. 8's just the magic number. So this little car here, 1, 2, 3, 4, 5, 6, 7, 8, it's got 8 electrons in there. It's all full up. Doesn't want this other electron that's running trying to catch up with the car. So if the electrons or if the elements are able to bond with other elements that will complete the outer shell and allow for it to have 8 valence electrons, then that makes the elements really happy. We're going to do a couple examples of Bohr models together, but first let's look at what are the instructions on how to make a Bohr model. So these are really easy to make. The first thing that we're going to do is we're going to figure out the atomic information. So we're going to use the periodic table, and we're going to figure out the atomic number, atomic mass, mass number, and protons, neutrons, and electrons. That's why we learned how to do that first. We're building on our skills. So we're going to draw the nucleus. Remember, the nucleus goes in the center. It's going to have your protons and neutrons. And after we draw the circle that represents the nucleus, we're going to put the correct number of neutrons and protons in the nucleus. Now, sometimes within the nucleus, you may just see P for protons, and it'll have a number beside that indicating the number of protons, and an N for neutrons, and then the number of neutrons listed beside it. Sometimes you'll see circles drawn out inside the nucleus, and those circles will also represent the protons and neutrons. The circles with a plus sign in them will, of course, be protons, and then the neutrons are usually indicated by an open circle or a shaded circle. So after we put the protons and neutrons in the nucleus, we're going to start putting the electrons on the Bohr model. So we're going to draw the first orbital shell, and then you'll fill that one up with your 2 electrons, and then we'll continue drawing additional orbital shells as needed. So you only draw as many orbital shells as you need. And keep track of how many electrons you're putting on the orbital shell so you know how many you have left to place onto the orbital shells. Here's our first example. So in your notes, we're going to record the atomic information, and then we're going to draw the Bohr model. So we're doing boron first. Boron's chemical symbol is B. The atomic number is 5. Atomic mass is 10.81. Mass number is 11, so 10.8 rounds up to 11. Number of protons is the same as the atomic number, which is 5. Number of neutrons, this is where you do a little math. Mass number minus the atomic number, so 11 minus 5 gives you 6. And our number of electrons is 5. So remember, ape man, your abbreviation, APE, atomic number, is the same as the protons, is the same as the electrons. So down here at the bottom, I have put the amount of electrons that each orbital shell can contain, and that way you can use that for a quick reference. So the first thing that we're going to do is draw the nucleus. There's our nucleus. And we're putting our 5 protons and our 6 neutrons. So it's not necessary to draw the circles in there representing the protons and neutrons. It takes a long time to do that, and we're just going to be concerned mostly with the placement of the electrons. So we have 5 protons and 6 neutrons. Now we need to put our 5 electrons on the orbital shell. So we're going to draw our first orbital shell. Remember, it can hold up to 2 electrons. There's 1, 2, and we need 3 more electrons because we have a total of 5. So we draw our second orbital shell, and there's 1, 2, 3. So now we have a total of 5 electrons. Lithium is our next example. Our chemical symbol for lithium is Li. Atomic number is 3. Atomic mass is 6.941. So that's the information that's just contained on the periodic table in the screenshot that I have there. That's directly from your periodic table. Mass number 6.9 rounds up to 7. Our number of protons is the same as our atomic number, which is 3. Number of neutrons is 7 minus 3, so that's 4. And our number of electrons is 3. Remember, we're going to start out drawing the nucleus. So there's our nucleus, and we're putting 3 protons and 4 neutrons. We need 3 electrons on this Bohr model. So we're going to put our first orbital shell, and we're going to place our 2 electrons on it. Now we just need 1 more. So we draw our next orbital shell, and there's our 1 last electron. So now we have a total of 3 nice pink electrons. Next example is fluorine. So fluorine is chemical symbol F. Atomic number 9, atomic mass 19.00, which rounds to 19 for our mass number. Our number of protons is 9, neutrons is 19 minus 9, which is 10, and our number of electrons is 9. We're going to start off with your nucleus, so there it is, and we're putting our 9 protons and our 10 neutrons. First orbital shell is going to contain our 2 electrons. Now that means, since we need 9 electrons, that we have 7 more electrons to place on our Bohr model. So we're going to have to jump to our next orbital shell. And remember, it can contain a maximum of 8 electrons. But we don't need 8 electrons on there, so we're just going to place our 7 electrons. And that will give us our total of 9. So fluorine has 7 valence electrons. So we're going to do 2 more examples in your notes. We're going to look at phosphorus, which is atomic number of 15, and potassium, which is atomic number of 19. So try those on your own and use your periodic table to help you.